Hello, welcome to today's class. Today we're starting with chapter 3, and then in today's class we are going to look at how to examine relationships between categorical variables. In the previous chapter, in chapter 2, we understood what categorical variables are and also what numerical variables are, and also the appropriate tool to use to display those types of data. In this chapter, we are going to examine the relationships or the associations between two categorical variables. And so by the end of this lesson, you should be able to understand what marginal and conditional distributions are. You should be able to identify a contingency table when you see one, and then also understand what the Simpson's paradox mean. And then also, whenever you have a contingency table, you should also be able to answer some questions about them. So a contingency table is a table that displays the frequencies for combinations of two categorical variables. So for example, when you look at this table here, this table here is an example of a contingency table. And so what are the categorical variables here? The categorical variables here are two. The categorical variables here are gender. This is male and female, so that is gender. And then this is for pets. And so the table displaying the frequencies of these two categorical variables is what we call a contingency table. And whenever you have a contingency table, you should also be able to identify what are marginal distributions and also what are conditional distributions. And so for marginal distributions, so like I told you, the distributions, the variables here are gender and then pets. And so these numbers here are these are the marginal distributions for pets. And then these are also the marginal distributions for gender. I repeat again. So these numbers here are the marginal distributions for pets, and these are the marginal distributions for gender. So for example, if you're asked to find what is the marginal distribution for gender, all you need to do is to do male equals 60 over 125, and then female is 65 or 125. So that is what a marginal distribution is. And then also for conditional distribution, so for example, this here is a conditional distribution for gender for people who has dogs. So this is the conditional distribution for gender for people who has dogs. This is the conditional distribution for gender for people who has cats. And so these are the official definitions for marginal distributions and conditional distribution. So as you can see, conditional distribution, we find that distribution of one variable given the other variable is fixed. So for example, you can see this one has dog is fixed. So that is what marginal distributions and conditional distributions are. Now we have this example here. 200 adults shopping at a supermarket were asked about the highest level of education they had completed and whether or not they smoke cigarettes. And so what the researcher wants to do is to be able to determine if there is an association between smoking and level of education. So this is the data, and then this data is available on StatCrunch. So we load this data. But before we do that, let's try, so we have this data. Let's try to answer certain questions about the data before we get to StatCrunch. So now let's try to describe the W's. We've learned the W's in chapter 1. The who, the what, the where, when, how. And so if in any of them we do not have any information, we should state that it is not specified. So now let's look at the data here. Who? The who is what? Is the 200 adults. Is that okay? What was recorded? Smoking status and also what? Level of education. Where? Supermarket. When? Wasn't specified. How? It wasn't also specified. And then why? To determine if there is an association between smoking and also level of education. So these are the answers for that. And then the other question is also, is this data categorical data? Yes, it is. Remember, smoking and then level of education, they are categorical. These numbers here are the what? The frequencies. The first question we want to ask, does this overlap? No. So does it mean like somebody can smoke and not be a smoker? No. So the first question we want to answer is that what percent of shoppers were smokers with only high school education? What percent of shoppers? It's very important to understand what percent of shoppers were smokers with only high school education. So now when we look at our table here, the question is what percent of what percent of shoppers? How many shoppers do we have? We have 200. Were smokers with only high school education. So it's going to be 32 over 200. That gives you this one. Then the next question is that, so I want you to think about this one and answer that. What percent of shoppers, what percent of shoppers with only high school education were smokers? What percent of the shoppers with only high school education were smokers? So I'm giving you a few minutes. So think about that and then let me know. What percent of shoppers with only high school education were smokers? We are looking for what percent of shoppers with only high school education were smokers. So now let's look at our table here. We are looking for what percent of shoppers with only high school education were smokers. So the people with only high school education are 93. And what percentage of them were smokers? 32. So it's 32 out of 93. And then the other question is that what percentage of the smokers had only high school education, what percentage of the smokers, what percentage of the smokers had only high school education? How many smokers do we have? We have 50 smokers. And how many of them had only high school education? 32. So that gives you 32 out of 50, which is the same as 64%. The other question we want to answer is that, is there an association between smoking and level of education? So what they want to understand is that, so for example, you see high school, 2-year college, 4-year college, as your education is becoming higher, are we having higher level of smokers, or the level of, or the number of smokers is decreasing? So how can we do that? So for example, so we see in high school, there is about 32 out of the 93 people were smokers. So that is what I have done here, which represent 34%. And then for 2-year college, we had about 5 out of 22 people were smokers. So you can see the percentage is what reducing. And then with 4-year college, we had about 4 years, so that is 13 out of what? 85 people, which gives you 15.3%. And so you can see that the percentages are different across the various levels of education. And so we can conclude that there is what this data provide evidence that there is an association between smoking and education level, because the percents are different across for different levels of education. We will load this data in StatCrunch and also analyze, or try to also compute the row percent and also the column percent in StatCrunch. So to compute the row percent is 32 over 93, 61 over 93. That is a row percent. Column percent, you're going to get 32 over 50, 5 over 50. So that is how to compute both row and then column percent. But we don't need to do this because StatCrunch does that for us. The thing that we have to be very careful is that we have to be able to understand the wording. What denominator are we using? And then also we have to make sure that what we examine all the variables, we have to look at both the marginal and then the conditional distribution. And then for now, we also need to have in mind that each category should have at least 5 members. And then we'll talk about Simpson's paradox next. So let's get to StatCrunch and then load this data. Yep. So we are in StatCrunch. So to load this, we go to data, and then we load from shared data set, and then we type in ED versus, I think it's SM. Let me check the data set. Yes, ED versus SM. We hit enter, and then there we go. We are looking for the one with Susie and Hall. So we see we have the data here. And so if we want to display the contingency table in StatCrunch, all we need to go is to go to Stats, go to Table, go to Contingency Table, and then we go to with Summary, because this table here is it has been summarized for us. So we go with Summary, and then our columns are smoker and then non-smoker. The row label is year. What do you want to display? You want to display row percent, column percent, and then percent of total. And then we hit compute. So that does that for us nicely. So this is the contingency table. So this table it has computed the row percent and then also the column percent for us. Okay. So now I want to ask you, what do you think is the best graphical method, or what is the best graphical way to display a table like this? In in our previous chapters, we learned about using pie chart and also bar graphs to display categorical data. But here we have two categorical data, and then we want to be able to display a graph that can be able to provide some meaning. So what do you think? Well, we could use split bar graph and also stacked. So let's see how to use split bar graph here in StatCrunch. So we go to graph. I think the book is also so you could use bar plot, but I used chart to do that. So I hit columns. And so what column do I have? I have smokers and non-smokers. And then I do my row labels here. I want vertical bars. So, and then I hit compute. So you see, in high school, so when you look at this, this is what? This is the split bar graph. So you can see these are the level of education here. So high school, 2-year college, and then 4-year college. So you can see high school, the one in blue represents for the smokers and the non-smokers. So you can see the high school, the number of non-smokers were high. You can also see 2-year college too. And then you can see the smokers that's reducing. So you can also use this to also see if there is an association with that. We could also display stack. So to display stack, let's try to get here. And then we could also show vertical bars stack. And you see, this is how the stack looks like. So the blue is for the smokers, and then the red is for the non-smokers. The other thing we want to talk about is I want to explain what Simpson's paradox mean. And so let's do that right away. So Simpson's paradox means that when averages are taken across different groups, they appear to contradict the overall averages. So for example, I'm using this example here from the textbook to be able to explain what the Simpson's paradox is trying to imply. So for example, you can see in this table, we have two different pilots, that is Mo and then Jill. And then here is the on-time flight by time of the day. So this is the on-time flights by time of the day. And so when we look at this, even without looking at the overall, when we look at Mo, we can see that Mo during the day has about 90% of what on-time flights during the day, while Jill has about 95%. And so looking at the percentages, it looks like Jill has a higher percentage with on-time day flights. Let's get to the night one too. We can see for the nighttime, Mo is having about 10 out of 20%, which represent 50, 10 out of 20, which represent 50%. And then Jill has about 75 out of 100, which represents 75%. And so if we are judging based on these two um, columns, you might be tempted to say that, well, Jill is having a higher percentage overall because you can see that day and night, they are having Jill is having 95 higher in the day and also higher in the night. You might be tempted to say that. But then in reality, it's not because now when you look at it, you can see that Mo has higher number of flights in the day than Jill because you can see Mo is flying about 100. You see, and then jail also has a higher in the night. So what Simpson's paradox is that you see when you take averages across these groups, they appear, so you can see it appear to contradict the overall average because here you can see that it's with the percentages, it's looking like jail is higher. But with the overall, you can see here that he flies 100 during the night, during the day, and then 20 during the night. So it's 120. And on time for both of them is 90 plus 10, which is 100, which represents 83%. And when you look at jail, jail is also 120, but the on time for both the night and the daytime is 94, which represents 78%. So you can see that the overall average, it is more that has a higher on-time flight. So that is what the Simpsons paradox is saying. Now, this came about because sometimes when I was reading about it, like sometimes in colleges and admissions, people tend to say, oh, well, there is a lower admission rate for, say, females in, let's say, engineering and all that because of the percentages. But then so the research people did is that they also looked at the number of applicants, the number of female applicants. So then you have to be able to make a better comparison. So you just don't look at, oh, we had only 5 females as compared to, say, 15 males. And so we can say that, oh, so because of that, the males has a higher admission rate, but also you have to look at how many females applied. So for example, if in the College of Education or in the College of Engineering, say we had 10 females who applied and let's say 5 got admission, that is 50, right? And then let's say we have 1,000 males that applied and then 10 males were admitted, that is 10 over 100, that is about 10%. So you see, but then it's looking like we have higher number of males than females in the College of Engineering. So that is what the Simpsons paradox is trying to explain. I'll do a second video where we'll do a thorough example of how to do those computations in the contingency tables. So for now, I'll see you in the next video. Have a good one.